In this video, I'm going to give a brief introduction to hedging. So imagine the following scenario. We have a stock trading at 100 with a volatility of 20% and risk-free interest rates are 5%. With this information, we can price options using the Black-Scholes-Merton model. So for example, a one-year European call option with strike 100 on this stock is worth $10.45. Now, we could borrow $10.45 at the risk-free rate and buy the option. So we can represent this with the following assets and liabilities. We've bought the option, so that's an asset worth $10.45. We also have the liability, the borrowing of $10.45. We're going to assume we borrow that money for the entire year. So let's wait. So we'll do nothing, and we'll wait until the option matures. Now, the value of the portfolio in 1 year depends on what assumptions we make. So first, we assume we locked in the borrowing at 5% continuously compounded, so we have to repay $10.99. The option value, though, depends on what assumption we make about the value of the stock, or what possible values of the stock can occur in a year's time. The Black-Scholes-Merton framework assumes the stock is log normally distributed. Namely, the log return on the stock is normally distributed. So that's the natural log of S sub t, the value of the stock at maturity, divided by S. That has a normal distribution. The return on the stock, of course, is going to depend on our expected return for the stock. Now, if we assume that the expected return on the stock is equal to the risk-free rate, then the expected value of this portfolio in a year's time is 0. If we assume the expected return on the stock is greater than the risk-free rate, then the expected value of the portfolio will be positive. And if we assume the expected return on the stock is less than the risk-free rate, then the expected value of the portfolio is negative. So we have to make this assumption. Now, this picture was created by assuming this is a distribution of the P&L, or value in this particular case, because it started at 0. So this is a distribution of the P&L of the portfolio, assuming the stock was log normally distributed with expected return equal to the risk-free rate. Now the picture on the left is interesting. Basically, about 45% of the time, you lose that $10.99. The picture on the right is the same picture, except that we removed that spike. And so you can see when you actually make money. So there's about a 0.2% chance you're going to lose $10.90. There's about a 0.1% you're going to make about $13. There's about a 0.05% chance you're going to make $23, and so on and so forth. Now this is kind of an interesting distribution, right? We're looking at the distribution of our P&L of this portfolio, and what we see is that if we own this option, about 45% of the time it expires worthless. If we think about the value of this portfolio, and again, we're assuming the expected returns equal to the risk-free rate, the expected value is 0, but it has quite a complicated looking distribution. Now, we could also make some other assumptions. For example, let's say we follow the delta hedging strategy assumed in the Black-Scholes-Merton framework. In particular, we buy and sell the stock continuously, fractional quantities of the stock, so the delta of the portfolio is always 0. In this case, the portfolio is always worth 0. It has no variance. That's the whole point of the Black-Scholes-Merton framework, and that's where the fair value of the option came from.